Open up a 1.6 terabit optical transceiver module, the kind that connects GPUs inside an AI data center. And there's a single chip inside that accounts for about 30% of the entire bill of materials. Not the laser, not the photodetector, the digital signal processor, the DSP. At 1.6 terabit speeds, that chip costs over $150. There are dozens of these modules in every server rack, and every single one needs a DSP. The market for these chips is controlled by two companies, Marvell and Broadcom. And right now, DSP supply is one of the bottlenecks holding back the rollout of next-generation AI networking. If you look at the inside of an optical module, it splits into two zones, a persimmon. On one side, closest to the fiber connector, you have the optical components from the TOSI, which is the laser transmitter, and the ROSA, which is the photodetector receiver. On the other side, closest to the electrical interface that plugs into the switch or GPU, you have a green circuit board with a big black chip in the middle. That chip is the DSP. Its job is to sit between the electrical world and the optical world and make the translation work. Start with the receive direction. Light comes in from the fiber, hits the photodetector, and gets converted into a raw electrical signal. But that signal is messy, weakened by distance, distorted by the fiber, full of noise. The DSP takes that signal and runs it through equalization algorithms to reconstruct what the original data was supposed to look like. If you watched our SIR-DAS video, you already know that high-speed electrical signals degrade badly over copper traces. The same thing happens on the optical side, and the DSP is the component that cleans it up. Then there's the transmit direction. Data comes in from the switch chip through SerDes lanes. Those are the high-speed serial links we covered in the last video. The DSP takes that electrical data, encodes it into a format the laser can understand, typically PM4, 4 voltage levels per symbol, and drives the laser to fire the right pattern of light pulses into the fiber. And on top of both directions, the DSP runs forward error correction, FEC. It adds redundant information before transmission so that the receiving end can detect and fix bit errors without asking for a retransmit. At 200 gigabits per lane, the raw error rate would be unacceptable without FEC. The DSP is what makes it work. 3 jobs, signal cleanup, modulation, error correction, all running simultaneously across 8 lanes at 200 gigabits each. That's 1.6 terabits of data flowing through a single chip the size of a fingernail. A 1.6 terabit optical module has a power budget of roughly 22 watts. Go above 25, and you can no longer cool a 51.2 terabit switch chassis with air. The fans can't keep up. 22 watts for the whole module. The laser needs power. The photodetector and transimpedance amplifier need power. The control circuitry needs power. What's left for the DSP is about 7 to 8 watts. That's it. And in those 7 to 8 watts, the DSP has to run equalization, FEC, encoding and decoding, modulation conversion, and clock recovery across 8 200 gig lanes simultaneously. The computational density is comparable to a small GPU. The power budget is a fraction of 1. That contradiction is why optical DSPs have to use the most advanced process node available. Marvell's Ara platform is built on TSMC 3 nanometer, not because 3 nano makes the DSP faster, but because it's the only way to fit that much computation into 7 watts. The DSP is competing for the same TSMC 3 nano capacity as Apple's phone chips. And when module manufacturers can't get enough DSPs, the entire 1.6T optical module supply chain stalls. Marvell recently introduced a variant called Ara-T, a transmit-only DSP. Instead of handling both transmit and receive, it only processes outgoing data. The receive side gets offloaded to the transimpedance amplifier. The result is a module power reduction of more than 35%. Lumentum demonstrated this configuration at ECOC and hit roughly 16 watts for a full 1.6T module. That kind of power saving matters when you're trying to pack thousands of modules into an AI cluster. The optical DSP market is a duopoly. Marvell leads, Broadcom challenges, and almost nobody else can compete at this level. Marvell's position was built over generations. Nova in 2023 was the industry's first 200 gig per lane 1.6T DSP on 5 nanometer. Ara followed in T4 on 3 nanometer, lower power, higher integration, and now shipping in volume to hyperscalers. In March 2026, Marvell expanded the platform into 4 variants. Ara X with enhanced link reliability, Ara T for transmit-only mode, Petra as a gearbox that bridges 100 gig and 200 gig lanes, and Aquila M for campus-scale coherent light connections up to 20 kilometers. All 4 started sampling in Q1 2026. Broadcom fired back the same week. The Taurus BCM83640, also 3 nanometer, but with 400 gig per lane optical interfaces, targets the 1.6T module market from a different angle. And their Xeon 3 DSP goes head-to-head with Ara at 200 gig per lane. Broadcom has been shipping optical DSPs for years, with over 50 million 100 gig VCSEL channels deployed in production AI networks. But the competitive dynamic goes deeper than specs. Broadcom manufactures its own lasers, both VCSLs and EMLs. When Broadcom sells a DSP to a module maker, it's selling a kit. DSP plus laser plus driver, all designed to work together. Marvell doesn't make lasers. It sells the DSP as a standalone component and lets the module maker choose their own laser supplier. Lumentum, Coherent, whoever offers the best deal. Module companies like InnoLight tend to prefer that arrangement because Marvell isn't competing with them. Broadcom is simultaneously their supplier and a potential competitor. There's a third name worth watching, Credo. They come from the SerDes IP side and are pushing linear pluggable optics, an architecture that removes the DSP entirely to save power. At 100 gig per lane, that works. At 200 gig per lane, the signal degradation is too severe. You need the equalization and retiming that only a DSP can provide. For now, the DSP duopoly holds. Marvell isn't just building faster DSPs. They're assembling the full connectivity stack around them. Celestial AI for photonic fabric interconnect, XCon technologies for CXL and PCIe switching, Polariton technologies for next-generation plasmonic modulators aimed at 3.2 terabits and beyond. NVIDIA invested $2 billion into Marvell and pulled them into the NVLink Fusion ecosystem. The pitch is vertical integration. Own every layer of the connection between AI chips, from the SerDes lane on the switch die all the way to the photon entering the fiber. The risk is that vertical stacks are only as strong in their weakest link. If Polariton's modulator slips, the entire 3.2T roadmap is delayed. If Celestial AI's photonic fabric doesn't scale, the optical interconnect story loses a chapter. Every acquisition adds capability and adds dependency. Broadcom's approach is different. They don't need to own every layer. They need each product to be the default choice at its layer. Tomahawk switches have over 75% share in data center switching. Their DSP is deeply embedded in the largest cloud networks. The defense isn't integration, it's incumbency. The risk is different too. If a hyperscaler decides to build its own DSP, and NVIDIA has both the silicon design capability and the motivation to do it, Broadcom's customer becomes its competitor overnight. So the question this market is asking isn't really about which DSP has better specs at 1.6 terabit. It's about what happens at 3.2 terabit. Does the company that owns the full stack from SerDes to photonics have the advantage? Or does the company whose chips are already running inside every major cloud network hold the stronger position? That's the bet, and it hasn't been settled yet.